So last week we were going over the planets and also moons and asteroids, all those other things in our solar system. So now we're going to look out past our solar system, talking about exoplanets. So an exoplanet is a planet that is been detected that is around another star that's not our sun. So your warm question is, I want you just to guess, how many exoplanets do you think we have detected around, planets around other stars? How many do you think we've detected? Just take a rough guess. I want to see what you can come up with. And I just looked this up to get the correct number it said as of May 1st. So I guess I'm slightly off. Maybe I'm actually wrong. Oh well. But that'll be the number that we'll compare this to. But I want you to guess, okay? Legitimately, I'm just curious what you might think. So think about it, take a guess, and then we'll see. So your intuition might be that it's more than you think, and you're right, probably. So you might be, and I don't really know what you would think for this. Actually, I'm kind of curious. I'll be curious to check your answers for this, see what you were thinking about. Maybe a couple hundred, maybe like 1,000 or so. We have detected 4,260 exoplanets. I actually thought it was less than that. I thought it was actually closer to 2,000. But that's why I double checked. So, yeah, we've detected actually 4,260 exoplanets. Now, these planets come in a big variety of types, right? The smallest, I just checked this also, is a planet. It's only about twice as massive as the moon. So that's, quite small. That's smaller than Mercury. And the largest is like, I think 30 times the mass of Jupiter, but there's some idea that that might not even actually be a planet. It might be a brown dwarf, the failed star kind of thing. So that's a big range. We have planets that are so close to their stars that they orbit in hours. So yeah, a planet's year is like 4 hours, and there are ones where their planet's year is several thousand years, Earth years. So you got a huge range of everything. You have planets that are barely above absolute zero, and you have planets that are hotter than the surface of our sun. So you have an insane range of things in terms of what we've found. And so today I'm going to specifically go over how we actually detect these. What are we actually doing to figure out these? Now, there's a lot of methods that can be used, but there's two main ones that we've used the most to figure this out. So that's what we're going to focus on. So two main methods of detecting exoplanets. The first is actually the one that was also done first. You can describe this a few different ways. I've heard it as the radial velocity method. Why did I put a V there? But I've also heard it described. I also, when just looking at Wikipedia, it described it as the Doppler spectroscopy method, which is the same thing, honestly, even though it sounds completely different. The premise of this is that as a planet orbits around its star, the planet's gravity tugs on the star a little bit. Okay? So just like how, of course, the star's gravity causes the planet to orbit all the way around the star, the planet's gravity does cause the star to sort of wiggle around. Okay? Sort of, and again, it's kind of following the orbit, sort of. You usually can't see it, but if it's noticeable enough, so what can happen is that this wobbling can be seen through the Doppler effect on the star's light. Okay? So as the star's wobbling around, for a little bit of that wobble, it's moving toward us, and for a little bit of the wobble, it moves away from us. Okay? So the light that it emits is then blue shifted a little bit, and then red shifted a little bit, and then blue shifted a little bit, and then red shifted a little bit, like a continuous kind of pattern. And so from that, you can figure out a couple things. You can figure out first of all, by how quickly the pattern occurs, that tells you how close the planet is, because that pattern, it follows the orbit of the planet itself. So if the planet is much closer in, it orbits much quicker. Then the wobbling of the star matches that quicker pace. But if it's further out, then it's a lot much more of a slower wobble. So the rate of that can tell you how far away it is, and then the actual amount that it's pulling. So in other words, the disparity between, like, again, if the red shift versus the blue shift is really really small, I mean, all of this is small, but if it's like really small, then the mass of the planet itself is not going to be very big. But if it's a bit of a bigger difference between them, then it's going to be a larger planet. So this method lets you tell how far away the planet is from its star and how massive it is. Okay, so it tells you those two methods. So this method lets you find a planet's orbital distance and mass. Okay, and I have a GIF to actually show you this. Oh, here. So you can see as the planet's going around the star, you see here's the spectral lines in the star. You see the star's wobbling. This is, of course, an exaggerated example, but the star's moving, and so here, I guess the idea is that we're over here, because as we're observing the star, see now it's moving away from us if we're over here, so the light gets red shifted, and then it gets blue shifted as a star moves towards us, and so the amount that this light moves back and forth is determined by the mass of the planet, and how quickly it moves back and forth is how close the planet is. So this was actually the first method that was used, and it was the first planet was actually detected in 1992 from this. It was actually data from like a few years earlier, but they just didn't know what it was from. And then someone kind of figured out, hey, this would happen if a planet was going around the star like this. And so then they looked back at some old data and were like, oh, hey, here was a planet that we totally didn't even know was a thing. I believe this first planet, I might be confusing it, but I think this first planet was a planet known as 51 Pegasi b. 51 Pegasi being the name of the star, and then we're really creative that, B is just the planet. Exoplanets are always named like B, C, D, E, E, just like through letters. Based on order of discovery. They never use A. I think they use A as the star, which, okay, whatever. So anyway, 51 Pegasi b, the planet I'm not sure how much bigger, but it's bigger than Jupiter, and it orbits its star in 4 days. Again, compare that to Earth, or compared to Mercury, which orbits its star in 88 days. So you have this Jupiter-sized planet, bigger than Jupiter, that was orbiting really close to its star, and it was really hot. So yeah. Now because of this, this is hard to see if the planet is further away or if it's smaller. So this is true for the pretty much all star detection methods for the exoplanets, but it's easiest to detect planets that are large and close. Okay, which just close to its star. Well, also, if the star is closer to us, then it's easier to see as well. So that's sort of like it's kind of the main thing where it's like, okay, great, we can see Jupiter planets that are like scorching hot. Hooray! It's not great in terms of like if you want to find aliens, but I mean just in terms of expanding what we know about space, like that's really interesting because previously we thought giant Jupiter-sized planets very close to stars was impossible. So it's interesting. Anyway, you have actually the tools to sort of figure this out and sort of do math from this. It's just there's a lot of steps involved because we have the Doppler shift formula. So we can use that to find velocity. And then if you find velocity, you can kind of pair that with like gravitational kinetic energy and gravitational potential energy and solve for mass that way. Yeah, so it's not super pleasant, but you could do it. At least do some sort of approximation. But this is not the main method we use anymore, so I'm going to actually kind of drop this and then we go on to the next method. The next method is known as the transit method. The transit method is that as a planet passes in front of its star, it blocks a little bit of the star's light. Okay, a little bit of the star's light. We can see this as a dip in brightness. And here's the key, it can't just be a one-time thing, it has to occur with a pattern, right? Let's say, oh, the star dipped for, a little bit, and then A month later, oh, it dipped again by the same amount. Another month later, oh, it dipped again by the same amount, right? That tells you it's a repeated pattern of a planet going by. Otherwise, if we just see a random dip, well, that could be just, I don't know, some random dust cloud just moving by, right? You know, it doesn't have to mean a planet, right? So, that occurs repeatedly if it's an orbiting planet. Okay, now here, similar to the radial velocity method, how quickly this occurs is related to, again, how far away the planet is from its star. So again, this method lets you find a planet's orbital distance, so that's still the same. But the amount of light that the planet blocks is actually not dependent on the mass, it's dependent on the size, the actual radius, or I guess technically the area, right? You think of it like a shadow, right? You have when we look at a star, we see the star as a disk, right? Obviously, it's a 3D sphere, but we see it as a disk because that's how we're looking at it. Now, we put a smaller 3D sphere crossing in front of it. It's basically you have a small circle blocking out a part of a bigger circle, right? So that lets us find the orbital planets and radius. Okay. Now, if we can use both of these methods, we can then find the mass and the radius, and we can start calculating stuff like density, gravity, like surface gravity, and stuff like that. So that's a little bit more information from there. But from this method we can find it. And radius usually is like good enough because, granted, of course, there are planets that have similar radius where their masses are noticeably different, but you're not gonna have a situation where like there's a planet the size of Saturn, and like let's say you have two planets that we say, oh, this one has a radius of, these both have radius of about Saturn. One of them is gassy and one is like the Earth. Like that's not a thing. So while there is a bit of variance with mass and radius, it's not a ton, so you can usually, with decent certainty, kind of predict, okay, this planet, based on its radius, should be gassy, this one should be rocky, and I'll explain more about this later, because there is a bit of wiggle room in there, and there, of course, there's the question about, like, well, where is actually the boundary between that, which, again, I'll talk about that later. So, the transit method, though, we're actually going to kind of use some math on for this. So, total distance radius. So, in terms of radius, here's how this works. Again, you have, I have a gift for this too. Okay, here. So you can see, here's like the brightness of a star, and then as the planet crosses in front of it, it blocks some of it, and then as it goes away, it goes back up. Now, granted, these graphs in real life are way more fuzzy, right? A star is not perfectly even. There's sunspots on it. I mean, you can see this image. It's not like exactly it's a perfectly uniform thing. So this graph is always sort of wiggling around anyway. And then when it drops down, keep in mind that this dropping down is usually like really small compared to the size of a star. For example, if you do this with Jupiter, and I'll show you the math-wise how this works, you end up with like the sun being only blocked by like 1%. So it's a very, and Jupiter's giant planet. So that's sort of the issue, is that you're trying to find a very small pattern in data that's already pretty noisy. So that's sort of the difficulty with this. And of course, if you get to smaller planets like the Earth, it's even smaller of a difference. So that's sort of the challenge with that there. But you can see what matters is you have this, the disk of the star that we see, and then the disk of the planet that goes behind it. So this dipping that we see, here's the amount of light, it dipped down by a certain amount. That dipping is caused by the size of this disk of the planet compared to the disk of the star. So what this means is that the formula for this is actually fairly simple, at least, again, the base approximation for it. It's this here, and again, I'll explain what the terms mean in a second. I mean, you could probably guess what the R's mean, but here's what we have. So delta F is your change in light detected as a decimal. Okay, so what this means, so in other words, a 1% decrease is 0.01. Okay, and this is, we don't worry about negatives, right? So if there is a 1%, if I say, the star's light decreased by 1%, that means delta F is 0.01. It's not negative or anything like, or it's not negative. It's also not it's not there for, oh, if it's a 1% decrease, that means now it's 99%. No, it's the actual change. Okay, so the change is what the delta F is. And then R planet is radius of transiting planet in meters, and then R star is radius of star in meters. Okay, so pretty straightforward in that sense there. Now we could do, let's see. So let's do sort of an example here of, again, 1%. Sort of what does that look like? Okay, so if you have, you're looking at a star and you say, okay, I see the light dips by 1%. How big is this planet then? Okay, well then your delta F becomes, again, 0.01. That would be then radius of planet. And let's just say we're talking about the sun. Okay, so there's another star, let's say it's exactly the same size as the sun. What do we kind of get? So then you put in the radius of the sun, which is that there. And remember, it's squared. All these are squared. So we have, let's see. Okay, so I want to square that. So 69550 squared. That lovely mess. Okay, 4.8372. That is into the 16? No, 17, right? Because that's 3. Yeah, okay. So we get 0.01 equals R planet squared divided by, what was it? 4.8372. 4.8372 times 10 to the 17. Okay, so then you're going to multiply that up to combine it with the 0.01. So you get, well, this would just, times 0.01 is the same thing as divided by 100. So this becomes 4.8372 times 10 to the 15 equals R planet squared. And so then you would square root this. So let's see, divide by 100 and then square root it. Okay, so you get 6.955 times 7. You may notice that this is the same thing as just 10% of the star. And so that makes sense if you have 10% of something. So in other words, our planet divided by our sun is 0.1. Well, you're squaring both of that. So 1/10 squared is 1/100th, which is what this is. So this is like a very simple example here to kind of see this works. So this size, if you're curious, this is about the radius of Jupiter, I believe. Radius. Okay, average radius. So this is, yeah, again, it's in kilometers. You'd add another 1,000. So 6.9911 times 10 to the 7. So yeah, almost the same thing. So Jupiter is about 1% of blocking of the sun. And yeah, let's do something a little bit different. Let's say we have, let's say, well, we can also do something that's kind of opposite this. So let's say, make something up here. Like, so, okay, we solved for planet radius. Let's solve. Okay, let's assume. No, okay, I'll just do it this way. A planet blocks, let's say 0.5% of the light of a star that's you know what, let's say 10% the size of the sun. Find the planet's radius. Okay, so now, again, we're going to use the transit formula. Now we just have to be careful about the numbers that we plug in. So again, we're solving for the planet's radius still. Delta F gets 0.5%. That means delta F, again, it's as a decimal, so it's 0.005. Okay, because again, I have to use it as a decimal. Equals R planet squared divided by. Okay, so now we want something that's 10% the size of the sun. So this is the radius of the sun, so we want 10% of this, which would be times 10 of this, well, this number again. So 6.955 times 10 to the 7. Wait. Yeah, okay. So let's see, we get. So actually, we already have that number, which is convenient. So I want to square this, and that's just going to be that number. So we have 0.005 equals r planet squared 4.8372 times 10, 10 to 15. Okay, multiply that over. Okay, and you get, right, so you have, wait, let's see, 3, 6, 9, 12, okay, 13, so 2.4186. 13 equals r planet squared. So r planet equals, let's say 4.918 times 10 to the 6. Hmm. One thing that I also always like to do for this, because if you just stop at this number, it's kind of like, okay, I have the radius of the planet, but like, how big is that? I don't know, right? Like, it's just a number. I don't know how to compare that. So what I like to do is always divide this by the radius of the Earth, because then you get your mass, or your radius and Earth radii, and that helps you understand the number better. So let's do 4.918 times 10 to 6 divided by 6.371 times 10 to the 6. So we're just doing this to sort of get a sense of this here. So 6371 No, not that. Okay. Okay, so 772. So this means that if you have a planet that's 77% of the size of the Earth and it's orbiting a star that's 10% the size of our sun, it will block 0.5% of the star's light. Okay, so this is a way of kind of helping you kind of figure this out. So this is the idea about finding radius, and again, from radius you can often find some things about mass. Again, for example, this planet, it's smaller than the Earth, it's going to be a rocky planet. This planet up here, well, this is basically Jupiter. It's going to be a gas planet. You can kind of figure out from that. Now, the size of the planet is one thing, but you also want to know how far away it is. So, the way this works is that you can figure out a planet's orbital radius by noting the frequency of the dimming. Okay, so let's say this planet here. Let's say the 0.5% dimming occurs every, I don't know, say 10 days. Okay, it occurs every 10 days. So this means that therefore, if the dimming occurs every 10 days, the planet's orbital period is 10 days. Can't type. Okay, is 10 days. So, now if you remember, back to first semester, we had Kepler's laws. So if we know the orbital period, we know how the orbital distance. So remember, there was Kepler's third law, which was that the orbital period squared was equal to the semi-major axis cubed. Now, I specifically told you when we did this that this only works for things orbiting the sun. Now, these are planets that orbit other stars, so then you think, well, then this doesn't work. The thing is, it does work if you modify this by dividing it by mass of star. But the key is, the mass of the star is in solar masses. Okay, so that's sort of the key. Because otherwise, think of it this way: well, if you had this for something orbiting the sun? Well, what's the mass of the sun in solar masses? It's 1, right? So then you're just dividing this by 1. It doesn't change anything. But again, the key for this also is that the period had to be in years. So we can figure out how far away this planet is, but we need to know the mass of the star in solar masses. And I don't know, like a star that's 10% the size of the sun. How big of a mass would that be? Like, I think it's because again, its radius is volume 1,000th. Seems like that's too small, but screw it. Let's say 1,000. So let's say the star mass of the star is 1,000th. So in which case, let's say we want to know the distance. So the years in this example, well, it's 10 days. Look, in the Earth, you can usually just say it's 365 days. So if we want to know the time in years, well, it's going to be 10 divided by 365. So basically, if the planet orbits every 10 days, how many Earth years is that? So 10 divided by 365 gives you, 0.0274. Okay. ASM we don't know. That's what we're solving for. So let's say M star. Let's say it's 0.001 M solar masses. Okay, let's say what that is. That's what that is. I'm making that up. I'm not 100% sure. So let's solve for this now. So we have 0.0274 squared equals semi-major axis cubed divided by 0.001. Okay, so first thing, let's square this. Okay, so we have 0.00075. I'll add 0.6. Okay. Equals a. Okay, so then you multiply that by so then times 0.001, which gets you, just more zeros in front. So you get 0.222. And then you have to cube root this. And when doing so, let's see, you get 0.0091, I'll say. Again, your answer is an AU. Now, you might think that seems really close. And yeah, it would be. But again, remember, your star, it's 10% the size of the sun, so you kind of want to be close in this example, again, if you're trying to get something with life. And now, let's see, you know the orbital distance, you know the size of the star. Now, if you have the temperature of the star, you can find the equilibrium temperature. So, let's say the temperature of the star is, let's say it's 3,000. Okay, that seems reasonable for this type of star. So, find the equilibrium temperature. Okay, here's our formula. Bit R star divided by 2R orbit. Okay, so we want to solve for TEQ. Now, T star, again, I just gave you as 3,000. R star, we have that. It was 10% of the sun. So, and we need this number in meters, though. So that was going to be, well, 10% of the sun is the 6.955 times 10 to the 7. That's what that was. Okay, then we're dividing by 2 times the orbital radius, but again, this also has to be in meters. So we got the answer in AU here, but we have to convert this to meters. So we have to multiply this by 496 times 10, it was to the 11. You get till this one happiness. This is 1.36 times 10 to the 9. Meters. So that's what you're going to put in here. And close that off. So we have, okay, so we're going to multiply this by 2. 2. And then divide by that, but then you're flipping it. Okay, so everything, that's what's in this parentheses. Okay, so we have DEQ equals 3,000 times this 0.0. That's not a great number to round. 0.02 5577855. That's what's in the parentheses. That's what's in the square root. So then you square root it, which basically is 0.16. Okay. and then times 3,000. 479.8 Kelvin. Which, if we want to just do the conversion to other things, it's 206.98 degrees Celsius, or 404 degrees Fahrenheit. So in this example, this planet is not going to have life on it. It's over 400 degrees Fahrenheit on average. So the numbers I picked for this, again, I just randomly guessed these numbers in terms of the mass of the star and the temperature and whatever. So, you know, but yeah, this planet would be too hot. But hey, now you know that, right? And so think about this. This is actually kind of impressive, the amount of information you have. As long as you have information about the star, right? So the star's temperature, the star's mass, and the star's radius. And just if you have those three things, and you can look at the transit graph, and you can see, okay, it dips by this amount, this often, you can then calculate the planet's radius, its orbital radius, and you can approximate its temperature, which is really powerful if you think about it. You have all this power in your hands with, fairly simple math. Again, like, the numbers are not great, but that's just sort of the nature of how this all works. And again, when I say fairly simple, it's not calculus, right? You don't need to worry about stuff like that. So, yeah, that's pretty impressive that we can do that. Anyway, tomorrow I'm going to have a kind of sort of a practice video with this kind of stuff. And I'm actually going to show you some actual graphs they're graphs that are made to show this as an example, but I'll show this to you and you can kind of see the process for working through this and getting a sense of how you can kind of get this together. So that's going to go for tomorrow. But in the meantime, you have a wrap-up question. Is somewhere down here. Where did you go? There you are. Okay, so your wrap-up question. If aliens were to use the transit method to try to detect the Earth, how much of a change in light would they detect? Okay, and I'm giving you the radius of the Earth and the radius of the Sun. So again, if they were detecting Earth, they would see, oh, this star, its light is dimming by blah amount every. Well, I mean, they wouldn't measure time in 365 Earth days, but you get the idea. So what would they see? So you're actually solving for delta F here. How much light decreased? So we have, again, the radius of the planet squared divided by radius of the star squared. So F equals, okay, radius of the planet. So that is 6371 squared divided by radius of the sun. Squared. Doesn't look good. It doesn't look good with the comments. Sorry, it's all wrong. Okay. Alright. Okay. So we gotta square both of these fun things. So 6371 squared gives you that. Okay. Then we have, I'll do 4.059, and that's 10 to the 12? No, 13, yeah. And then, oh, wait. Again, sun squared, we've done this before, that was up here. Yeah, 4.8372 times 10 to the 17, okay. So now we divide. So let's see. Divide by, I'll just squared equals. Okay, so you end up getting this. I think 3.9. Yeah, okay, so I'll just go delta F. It's 10 to the negative 5. Yeah, so that would be 0.1238484. That's your decrease in light. So in other words, when the Earth passes in front of the sun, it blocks 0.0084% of the sun's light. Okay, because again, remember how percentages work, right? So a percent is, you just lop off 2 zeros in here, and then you get to the percent. So that's a really small amount. So imagining you'd have to detect that difference in light. You'd have to detect that difference in light from something that's many light years away from us. And again, this also shows that this also is a lot easier if the star is smaller, right? So again, going back up here, this star was 10% the size of the sun, and here's a planet that's smaller than the Earth that blocked 0.5%. 0.5% is a lot easier to see than 0.0084%. Okay, and that's only because this planet is, or that star is 10% the size of the sun. It makes it much easier to notice that there's a planet that's even smaller than the Earth going around it. So that's sort of the challenge with all this kind of stuff, is dealing with that. So your homework question is sort of a practice with this. So the star Proxima Centauri, remember that's the closest star to us, it has a mass 0.123 times that of the sun, radius 0.141 times radius of the sun, and a surface temperature of 3,042. These numbers are actually, I looked them up, so those are actual numbers. I didn't just make them up like the previous mass ones. And so if we witnessed a transit of Proxima Centauri and it dimmed the star's light by 0.558% every 11.186 days. So again, these are actual numbers for this. Therefore, there is a planet, Proxima Centauri b, around this star. So I want you to calculate the radius of the planet in meters and at Earth radii, the orbital radius of the planet in AU and meters, and then the equilibrium temperature. So basically what I just did with this theoretical planet here, you're going to do that with these numbers for Proxima Centauri b. So yeah, and this is, and I want you to kind of get notice that from the numbers you get, keep in mind that again, this is the closest star to us. So we have a star that is the closest one to us that has a planet that's, you'll find that the numbers are actually not that far off from Earth. So it's really interesting if you do this right, at least in terms of the planet's radius and its temperature. So that's your task at hand for today. So what do you do with that? Okay, again, tomorrow there's going to be more practice this kind of stuff, going through how this works. And then from there, we will transition into talking fully more about these different kinds of planets, what kinds of planets we think we have found to exist, and what this could mean for life outside of the Earth. So yeah, that's it for now.